My name is Jeff Melby, and I work at the U.S. Army Engineer R&D Center Coastal Hydraulics Lab. The title of this presentation is Improved Coastal Flood Risk Estimates Through Integrated JPM and Coupled Physics Approach. And this presentation is a follow-on to Abby's presentation on the Sabine Galveston Coastal Storm Risk Management System Design. My co-authors are Abby, Chris Massey, Shubhra Misra, Norberto Nadal Caraballo, Victor Gonzalez, Pat Lynette, and Alex Taflanitis. Sabine to Galveston study includes roughly 100 kilometers of coastal levees, flood walls, and closure gates in the Freeport, Port Arthur, and Orange County vicinities in North Texas. The project goal is redesign of the coastal storm risk management system to achieve consistent and lower regional flood risk. We also wanted to advance the state of practice with improved physics and statistics, and I'll discuss some of the details in this talk. This study was preceded by a complete planning study where alternatives and consequences were evaluated and the design selected. So here we're focused on the detailed element design. This shows a typical pile-supported T-wall in Port Arthur area. This area is roughly 20 kilometers from the open coast, but has a 1% annual exceedance probability, still water level of about 4.5 meters, and corresponding wave height of about 1 meter. So basically the area is exposed to very high flood levels and fairly small waves. This shows a typical levee, basically clay core, grass-covered, well-maintained levees. Abby discussed a general approach to the storm sim, probabilistic coastal hazard analysis, methods for tropical and extratropical storms. And in this case, our entire flood risk is driven by the tropical storms. And so we're limited to the tropical storm analysis. And the intent of the approach is to capture the full range of multivariate hazard probabilities accurately. And so for this study, Norberto constructed marginal distributions of tropical cyclone parameters from the HRDAT database dating back to about 1938. He efficiently sampled the distributions to develop a suite of synthetic tropical storms. And then Chris Massey modeled the storms in CStorm, which is ERDEX coupled hydrodynamic modeling system, which has ADCIRC coupled with ST-Wave as the heart of the system. The resulting wave and water level hazards were processed in Storm Sim to compute the wave and water level probability distributions. The ADCIRC mesh is shown there in the lower right, and it was very fine down to an element size of about 13 meters. The Corps evaluates risk for about 1,670 levee systems across the US, and overtopping with breach is the dominant risk driver. While extensive geotechnical and structural designs are done, the coastal storm risk management crest elevations are based on risk of overtopping induced breach. Our study included expanding the Storm Sim software system to include levee and flood wall responses such as overtopping, forces on walls, and map geometry within the stochastic simulation system. For all these analyses, we included computation of epistemic uncertainty. And this slide summarizes the main contributions, including unresolved variability of Holland B, hurricane structures, and hurricane tracks. Astronomical tide was considered an uncertainty because it's small. Skill of the hydrodynamic model, ADCIRC and ST-Wave in particular was quantified, and ADCIRC predictions are shown in the upper right versus high water marks, and you can see quite a bit of scatter there. Skill of overtopping model and pressure models were quantified and included in our stochastic simulation. We sampled uncertainty in the Monte Carlo simulation, and you can see the results for the still water and wave height in the lower right corner for one specific point for the different sea level rise scenarios. And basically we're characterizing the uncertainty with confidence limits. And in this case, we're plotting two. The 50% is the black line and the 90% confidence limit is the red line. This slide shows the 1% annual chance, annual exceedance probability still water level plotted on the ADCIRC nodes for Orange and Port Arthur. And as you can see, it's fairly consistent spatially, and it's pretty close to 4.5 meters. There's really endless challenges to a gigantic project like this, technical challenges. A few of the big ones I'm going to talk about today are listed here. And basically the hazard consists of combined wind, waves, and surge, and these processes interact nonlinearly. So we need to run coupled wave and surge models, but they're computationally expensive, so we want to optimize our storm suite. In addition, the inundation travels up to 45, 50 kilometers inland, a very high surge, relatively small waves, but you do get inland propagation of really low frequency waves because the energy across the surf zone and inshore is transferred to lower frequencies. So we need to characterize that. It's not well represented by phase average wave models. And then we'd really like the statistical estimates to be of the same accuracy as the physics. That is, we want to maintain the physics accuracy within our stochastic simulation, and that's not that easy to do. And so we spent quite a bit of time to maintain our multivariate probabilities and do that accurately in this study. As I said, we wanted to reduce our storm suite down to the minimum number of storms. We're spanning a very large area, so we have to have still quite a few storms. The coast of Texas required 660 storms in total. We reduced that suite to 189 storms. Using a metamodel based on a genetic algorithm. This technique was developed by Alex Taflonidis. And it matches the hazard curves nearly exactly. Here's an example for one save point where you can see the full suite and the reduced suite are nearly exactly matched. And this was very consistent across the entire region. The Nulli residual is defined as the difference between this linear superposition of water level components and the modeled values. And in this case, we're evaluating peak water levels modeled at specific geoid offsets in ADCIRC representing different sea level rise scenarios or points in time. And it's basically the beginning of the project, the end of the economic life at 50 years, and then 100 years. And as shown in the figure on the left, the Nulli residual for a specific storm is large, and it's actually greater than the linear offset. So this linear superposition is just not very accurate, and especially when you have inland flooding. On the right, we show all the storms plotted for specific points, still water level on the horizontal axis versus Nulli residual on the vertical. And offshore, the Nulli residual is small and well behaved, but inshore, it's very large and produces quite a bit of scatter. As I said, infragravity waves are fairly important for inland flooding because there's a massive energy shift in the wave spectrum as you go inland. For Freeport, where the flood risk management system is fairly close to the shore within several kilometers, these infragravity waves are fairly important. Pat Lynette used Cool Wave to model the complete wave spectrum. And so we were able to characterize the infragravity waves and then add the infragravity portion to the still water level to include that. In Port Arthur and Orange, the infragravity energy dissipated. So the ST wave actually produced a very good estimate of the waves for this area. There's lots of different stochastic simulation approaches. In this study, we looked at quite a few. I'm going to summarize that fairly quickly. Event-based are the traditional methods where you determine, for example, a 1% annual exceedance probability or 100-year event, that is wave height and water level, and then you compute your responses for those forcing statistics. It's a very simple approach. The problem is that you get a variable response probability, and so your risk is going to be variable. So it's really inaccurate response computation. A response-based is where you compute the response for every storm, compute the probability distribution of that response, and then use that to design your project. So it's accurate, it's spatially consistent, risk level, and the basic problem with it is it's more complex, but modern computer systems and modern software, we can make that quite easy. So we looked at all the methods in a comparison study. Up on the top right, I listed different methods in a flow chart, EB1, EB2, RB1, RB3. There was an RB2, but I won't talk about that today. But EB1 is the event-based simple method where you take for example, the 100-year wave height and water level and plug those into your overtopping equation and you get a response, single valued response. You can do it in a spreadsheet, very simple. EB2 is where the epistemic uncertainties are sampled in a Monte Carlo distribution, Monte Carlo simulation. So it's really doesn't solve any of the problems. It just gives you a better estimate of the epistemic uncertainty within the confidence limits. Response-based methods, RB1 was peak space. So we took the peak wave height and the peak water level and from each storm and computed the responses for each of those and then computed the probability distribution for response. And then RB3, we did a fully time-dependent analysis where we compute the response at every single time step of every single storm. And you can see a comparison down there in the bottom right. On the far right, we got a really good agreement between four of the methods, RB1, RB3, EB2, EB1. But that was fairly unique. We didn't get that very often. The plot to the left of that is more typical, where we get a wide variation, and especially at this 1% annual exceedance probability, which was our limit state. And here you can see the three different design limit states for overtopping rate. And so this is where we would design, and you can see that over the range of different methods, we get a wide range of overtopping rates. And so we would get a wide range of crest heights coming out of that. The event-based were always inaccurate for the most part. The three response-based methods that we used agreed almost, well, pretty consistently across all the transects. And this is because basically for the most extreme storms, the peaks line up in time. So wave height and water level occur at the same moment for the most extreme storms. So those probability distributions of response tend to align. So in this study, we ended up using RB1, which proved to be very accurate in comparison to RB3. So in summary, coastal storm probabilities are not well represented by the historical gauge record. It's too sparse in both space and time. So Norberto built synthetic events, tropical cyclones by efficiently sampling a tropical cyclone parameter, marginal distributions that were built on the historical data that's found in the HRDAT database. These were modeled with the coupled AdCirc ST-Wave modeling system and for all sea level rise scenarios. The coupled system is expensive to run, and so we reduced the storm suite using a genetic algorithm optimization system that matched the hazard curves. We ended up with 189 storms, but in some cases we needed to run some more simulations for some purpose or another. And if you're looking at a specific location, you can use the genetic algorithm to reduce your storm suite down to a range of 25 to 30 storms and get a very good estimate if you're looking at a specific location. Coastal processes are complex and nonlinear, require a coupled modeling system. Linear superposition is inaccurate. Surge inundates up to 4 meters or over 4 meters, up to 20 to 50 kilometers inland in this area. Swell and infragravity waves from the offshore don't persist that far inland, but for Freeport, where the system is fairly close to the shore, we did have to model infragravity waves with the Boost-Nest model. The event-based approaches produce large errors. And so in this study, we use a response-based method where we sample every storm and we compute the response for every storm. The peaks-based method was adequate for what we were doing. And that's it for today. Thank you very much for attending this talk.